Hello, everybody. Welcome back for a new episode of the Midnight Sessions. For those that are present live, um, just make sure that you can hear me well. You are seeing my screen. You can write on the chat is something uh, if you don't hear me at any moment. So I'm sometimes Discord plays fun with me. But okay, the procedure for this session is going to be pretty much the same as the ones that we were doing before. We are going through the ecosystem section, then we are going through some coding, and then I'm going to open the mics for anyone that wants to ask some questions, or they want to jump into the stage so we can discuss any topics. So perfect. This is part two of the last episode that we were going through actually creating transactions and analyzing what's going on while executing those transactions. So this part two, we are gonna now test the transaction using the Testnet network. In the last episode, we did the transaction using the undeploy network. So let's start. Let's first start with the academy. Uh, we normally we talk about the blogs and diaries as well, but since this is part two, we're gonna start with academy and hackathons. This is since there's a lot of topics to cover related to the academy. We're gonna continue studying where we uh, left it the last time. We were so here we have these modules. We are now on module number 3. We are understanding everything about zero knowledge proof. So last time we studied the key properties of zero knowledge proof. What is the difference between interactive and non-interactive? And now we're gonna keep on studying other topics related to the types of zero knowledge proof systems and the basic mechanics of zero knowledge proof. Okay, so we're gonna read this together, and as we read, I will keep explaining some topics. Okay, types of zero knowledge proof systems. Modern ZK proof systems vary widely in their performance, characteristics, and trust assumptions. This is a key concept: trust assumptions. Everything about cryptography, you have to assume and you have to understand what are the trust assumptions that were considered during implementation and research. While the boundaries between categories can blur, most systems can be compared based on 4 key factors. So let's see what are those key factors. The proof size. How large is a proof in bytes? Prover time. How long does it take to generate a proof? Verifier time. How fast can someone verify the proof? And the trusted setup. This one is really important. Does the system require a special setup ceremony which must be trusted to remain uncompromised? Later on, we're gonna analyze what are these parameters, trust assumptions for Midnight specifically, but just let's keep that in mind. Let's compare some notable systems. Okay, so now we're gonna list some of the proof systems available in the market. We have the Growth 16, which is a CK snark, very small proof, 200 bytes, and fast verification, but it requires a trusted setup that is circuit specific. That means each new application would need its own setup ceremony used in Zcash and some Ethereum ZK rollouts. So the main important part here is that each new application would need its own setup ceremony. Plonk, that uses CK snarks, a universal snark with a slightly larger proof and a slower verification at Growth 16, but it only needs a one-time trusted setup, reusable across applications. This makes this makes it more practical for ecosystems like Midnight. Halo 2 is an implementation of Plonk with a specific polynomial commitment scheme that supports recursive proof and avoids trusted setup when used with certain packets. So we use an implementation of Plonk, which is called Halo 2. This Halo 2, it allows us to do this recursive proof by using these specific polynomial commitments. And the most important part about this Halo 2 framework is that it's reusable across applications. So users can trust our applications. It's not us developers that are creating those trust setups, right? Somebody else created those parameters, and we are just using those parameters to create specific parameters for each circuit. Okay, let's see what are other proof systems available in the market. Bulletproof, no trusted setup, and compact for small statements. But proof size grows with the complexity of the statement, not succinct. So it's the word here that we were using, snark, it's because it's succinct, which this bulletproof is not succinct. So it's not considered a snark. Verification is slower, and proof size, it's around 2 to 20 kilobytes, becomes impractical for large programs used in Monero, right? We know that in Monero, we are actually able to transact coins, but in Midnight, we are actually implementing um, smart contracts that we can implement, we can set up, we can customize. Okay, another one, it's called Starks. Transparent, not trusted setup is important. You don't need a trusted setup. Post-quantum secure and scalable for provers. However, the CK property must be added explicitly, and proofs are large, 120 kilobytes. Verification is relatively fast, and they are great for batching computations on chain, off-chain, but less ideal for use cases like Midnight, where proof size and privacy guarantees are critical. So we Midnight, uh, it's really important to have a really small proof size, and we need to have these privacy guarantees. And and then, in short, while CK Snark and CK Starks are often contrasted, real-world systems blend ideas. Now, sometimes uh, there's other frameworks that they use specific features of each of those proof systems. Bulletproofs resemble the Starks in scalability and transparency, but aren't succinct. Plonk sits in the Snark family, but offers better trade-offs for general-purpose applications. For privacy-focused chains like Midnight, Snark systems with recursive capability and no need for per-circuit setup is ideal. Hence, the choice of Plonk-derived system Halo 2. So, why we are using Halo 2 for Midnight? They summarize these concepts here. It's we need to have recursive capabilities, and we no need for per circuit setup is ideal, right? We saw here that in for the case of Plonk, we are we don't but it only needs a one-time trusted setup. So we use these parameters when we are implement when in the future, at later on this episode, we're gonna be doing the coding part, and we're gonna see what these public parameters are, and then we customize those parameters to create specific parameters for each of the circuits that we're using. Okay, so now we know what are these proof systems about. So now let's take a look at some basic mechanics of zero knowledge proof. How it works, how it gets connected, how it's included in a system. Although the underlying math is complex, it's useful to have a high-level understanding of how a zero knowledge proof works. There are two parties: the prover, who possesses some secret information of witness, and the verifier, who needs to be convinced of a statement's truth. The approver wants to convince the verifier without giving away the secret. This is the main purpose of ZK. We we are going to be able to demonstrate something without disclosing that information. In a typical ZK proof workflow, the statement to be proven is formulated in a mathematical way, often as a problem or a circuit. That's why it's called circuits, because we translate a problem in a mathematical way, polynomials, and then we convert all that to circuits. The math, indeed, it's really complex, but Midnight is doing a really nice job to abstract that complexity so we can create those contracts and that logic using Compact, which is the Midnight DSL. For instance, the statement might be, I know a secret value that hashes to this public hash H, or I possess credentials that satisfies these conditions. Okay, let's keep reading here. Depending on the ZKP protocol, the setup phase plays different roles, but it always present. In all systems, both the prover and the verifier must perform a setup step to generate the proven and the verifying keys. Remember this setup ceremony that we were talking about? So this setup is for creating these proven verifying keys for a specific computation, a circuit. This setup ensures that both parties are aligned on what it is being proved. Before the circuit-specific setup, some systems also require a reference string, which may be a trusted. So we are now referencing the proof systems that we studied before, Groth and Plonk, meaning that if the reference string was generated dishonestly, security could be compromised. And then we have the transparent, like bulletproof and SARC, meaning it is derived from public randomness, like hash functions, and doesn't require trust. So we still depend on trust because we're using an implementation of Plonk called Halo 2. Nevertheless, these initial setup parameters, they were created once. So it was under following the correct procedures, security procedures, and based on those public parameters, we create those specific cryptography necessary for each of those circuits. So the typical flow is generate the reference string for trusted or transparent, run the setup for the specific circuit, producing the proven and verifying keys. We're going to see that later when we compile the circuits and we get to see those proven and verifying keys for each of those circuits. In our case, it's going to be for the counter contract that we created. Use those keys to generate and verify proof. The distinction is critical for security. Users should be aware that they may need to run or validate the setup phase themselves, specifically to verify that the tab they are interacting with is executing the logic they expect, rather than relying blindly on developer generated parameters. So this is something really important, since everybody can, depending on the proof system, generate those parameters. The user needs to have some means to verify that all that cryptography was set up and was developed and was implemented in the correct way. Uh, Otherwise, we can create whatever circuit that always passes that when we want to pass that circuit, even though the proof doesn't satisfy the conditions for the verifier. So all this setup, all these implementation has to be done in a way that us developers and users can verify. Okay, so the approver uses the secret witness and the proven key to compute the proof. The approver then performs cryptographic computations like elliptic curve operations, polynomial commitments. This is the math underneath how all this works, combining the witness and the public parameters to produce a concise proof. This proof might be just a few hundred bytes, even if the proof's knowledge of a very large or complex secret. That's why it's snarks. In essence, the prover is attesting that they know some secret that satisfies all the conditions without showing the secret. Now, the verifier then uses the corresponding verification key and the reference string to verify the proof. If the proof is valid, the verifier is cryptographically assured that the statement is true. The prover does know a valid circuit witness. So here we have a graph that connects all these things that we just read. The prover generates a proof using this proving key. The verifier is gonna receive that proof that was sent by the user, and using this proof plus the prover's statement plus the verifying key, we are going to be able to make sure if the prover's statement is valid. Okay, perfect. So this is about the zero knowledge proof. The flow, it's really simple. How it works, it's really simple. The implementation and the mathematics underneath, it's really complex. But as I mentioned, Midnight did a really nice job for us not to worry about that that implementation. We're gonna use just some APIs and a DSL compact for writing our contract, and that contract is gonna get compiled to JavaScript so we can use it in our tabs. Excellent. So now let's take a look at the hackathons. These hackathons are really important. We're gonna discuss why, and we're gonna see what are the hackathons available right now. So we have this official page on the documentations of Midnight where they list all the hackathons available at the moment. So we can see here that they say join a Midnight hackathon. They give some description, and then they list the hackathons that we have available right now. So the way these hackathons are working right now is that we're gonna have a live hackathons and we're gonna have in-person hackathons. It's virtual hackathons and in-person hackathons. These virtual hackathons are those ones that we're used to it, right? Those that have been participating in the past, myself included. I participated on these virtual hackathons. You don't need to be in a specific place. You just can develop your application on your country, in your city, and then you just deploy on the cloud and send the GitHub link to the judges. So this is virtual hackathons, and the in-person hackathons. These are hackathons that are they take place in a specific place. Normally, there is a venue that people go to, and they have some conferences. You deploy your application, and at the end, you present your applications, and they have the winners. The virtual hackathons, it's kind of a more complex hackathon. They have different purposes. The live virtual hackathons is more for developers to learn to connect, to network with other developers and the Midnight team itself, and deploy an application following specific rules. The in-person hackathons are more like a get to know the technology kind of hackathon, right? It's more like a ideation process, because hackathons, they normally last 2 days. So it's a really short time where developers write a really simple code, but specific, and kind of it's more like an ideation because it's less time than the virtual hackathons. These virtual hackathons are lasting 2 months. So we have now one live that it's called Midnight Mini Dab Hackathon. So this is the topic of the hackathon. Let's see what they say. The Mini Dab Hackathon invites you to build small, powerful applications that highlight a single feature or use case of the Midnight protocol. This hackathon is your chance to explore the playful side of privacy. We are looking for submissions that are bold, uh, whimsical, and little unexpected. So bring us your wild ideas, your mini masterpieces, your single feature apps. So this is important here. Mini masterpieces, single feature apps. What they're looking for in this hackathon is not like really complex and end-to-end applications. It's just a mini dApp, as the title says, right? Just focus on one feature, one specific masterpiece, something that you might want to have in Midnight, and just solve it and present that small feature. So in this way, people are going to be able to go deeper in what Midnight infrastructure is all about and technology and solve one specific problem. And as I mentioned, the I really recommend all developers to participate in these hackathons, even though they don't feel ready. The the um, the importance of this hackathon is actually to learn, because you're going to be able to connect all your questions and all things that you might don't know. It's actually going to appear while you are developing the hackathons, because otherwise how would you know something that you're not gonna able to code. So that's why it's really well to just get hands on developing. And during these hackathons, you're gonna be able to connect with people. Right now, we have a lot of materials. We have examples, code. Uh, there is a Discord channel, and now there is a forum where people are writing all these questions. So in the past, sometimes when people were writing on Discord, questions can get lost, right? Because a lot of people are writing, but now they have this forum there where they are concentrating all the questions, and people have better follow up, right, for those questions, and everybody can see what's going on within the ecosystem. So I really recommend for everybody to join this hackathon. Um, so this hackathon ends in August, so there's plenty of time. It's 2 months. We have pretty much 1 month to go, and yeah, it's plenty of time for anybody to jump and start developing on this hackathon. Now, for the in-person hackathon, the one hackathon that we have confirmed so far, it's called the Midnight Hackathon Buenos Aires. This hackathon seeks to bring together the most talented developers from Argentina and Latin America to create innovative solutions focused on privacy. So this is going to be on Saturday, August 23rd to Sunday. So see, as I mentioned, normally these hackathons are 1 2 days long. So it's much less than these hackathons that they last 2 months. So the idea here is more ideation and networking as well within that that place, right? They're focusing this hackathon for developers in Argentina and Latin America, because since it's an in-person, normally people that are in that same country or really close by, they are managed to go to that hackathon, right? But at the end, everybody's invited, right? Anybody can go to this hackathon if they are willing to travel all the way to Argentina. Okay, what we have here, some winners of previous hackathons. Then here at the bottom, we can see here a summary, right? We have live hackathons, online hackathons, and in-person hackathons, and they have an option here to register. And if you click on each one of these, here we had a macro, right? A summary of these events. If we want to have the details, we just have to click, right, on these. We have an option to register, and we can click here on the titles where we're going to have all the summary. For example, this mini tab hackathon, if we click on that, then here we have all the hackathon overview. We have the hackathon details, requirements, see, duration 2 months, kickoff, submission deadlines, the prices, and everything that you need to know for registering and participating, right? Okay, excellent. Now we are gonna go to the catalog, where we analyze some partners doing some frameworks, products, and research. OpenZeppelin, they have been producing these token smart contract primitives to create a framework for tokenization. So what we're gonna do here is we're gonna take a look at the repo to see what they are doing and then start analyzing. For sure, this session is not gonna we're not gonna have time enough for analyzing all the repo. So we're gonna be analyzing each specific feature as we go through these sessions. Okay, so let's open the repo. I have already downloaded here. So this is the repo that we have for OpenZeppelin. Um, and they are following the pretty much the same structure and kind of framework that Midnight team is using to create a. We have a folder called Compact that we have here all the builder compilers for the compiler itself. So this is just a boilerplate for compiling contracts and specific instructions where to place the output of the compilation within the folders. So the main important here is the contracts file. So in here we can see that they have already developed different standards. For example, access control standards, archive standard. We're gonna see why they call it archive. We have fungible token, multi-tokens, non-fungible tokens, and ownable contract. They have developed so far these 6 type of tokens. They might include here more in the future. But for this session, let's start taking a look at one of these frameworks. So to start, we're gonna start with this fungible token. Okay, this fungible token it's an NFT as opposed to this non-fungible token that we know as NFTs. NFTs is normally one token represents something. You cannot trade different representations of the token since they are unique. Fungible tokens, it's kind of the tokens that we know that, for example, a currency, right? In a dollar, $1 is the same as the $1 that somebody else have. So you can swap between each name because it's the same, right? So this is fungible tokens. So let's take a look how they have implemented this fungible token. This is gonna be really nice to see because in Midnight, for those that are familiar with other blockchains, that I normally take as an example Cardano and Ethereum because Cardano works uh, as a local state. We have UTXOs, and in Ethereum we have this global state. In Midnight, we actually have both. We can have the kind of the local framework where we have representation of UTXO that we have already studied in CSWAP. Then we have a global state as well. But additionally, we have another feature, which is privacy and how everything gets connected. So all these frameworks are going to be really nice to see because we understand how different people might want to implement their applications. So the idea with these frameworks is for everybody to start at the same kind of using the same framework because wallets they're gonna show some information depending on the framework you're using. So you cannot create your own framework because otherwise then wallets might not display your tokens within your contract since you're not using the same framework. So right now all this is kind of we are in the discussion phase. Everything of this is gonna at the end be represented on a MIP. What is a MIP? It's a Midnight Improvement Proposals. So we have the standardization of different technologies. Okay, so we are here now in the discussion phase, and they are presenting this repo for their tokens, and we're going to take a look at the fungible tokens. So let's open these fungible tokens and let's see what we have in this folder. We have a source folder. This is just a boilerplate. And in here, we see that we have artifacts, we have tests, and we have witnesses. Let's see what we have in witnesses. This resembles a lot of the contracts that we were studying before, right? We have a contract and we have a witness. In this case, let's see what they have in witnesses. We can see that they have an empty oracle. So they're not using the private information for the tokens. So just by looking at the witness, we can take an idea so far that they are not using CSwap or they are not creating tokens in CSwap. They're just creating tokens on the global state in the ledger. Okay. Then we have this artifact. So we can see here that we have the outputs of the contract. We're going to take a look at that later. And then we have a test. So this test, this is something that we haven't studied so far in these sessions. And we're going to start taking a look at that on the next sessions where after we learn how to write the functions, how to run the circuits, and how to run the transactions, we have to study how to test without having to implement everything from zero and running a TUI and waiting for transaction confirmations. So we have test frame to test the contracts logic and to test the providers. So we're gonna take a look at this test later as well. So right now, what it's important for us, it's actually the contract itself. So under here, artifacts, fungible tokens, contract, we see here that we have the compilation of the contract, right? See, the index.js and the DCTS. We are looking for the contract itself, which is under test, and we have here the mocks, and here we have the contract. So here is the mock fungible contract. So we see here that um, we are using the language version of Compact 15. The latest one is 16. So they have been testing with a previous version. For sure, in the future they might upgrade their repo with the latest Compact language version. They're using the Compact standard library. Uh, this is something that we mentioned during the sessions. We haven't started writing the contracts themselves. We started with a really simple contract called counter. But for grabbing some additional functions, we're gonna need to import some libraries implemented by the Midnight team. So the name of that library is called the Compact Standard Library. And the way we import that is just by calling import Compact Standard Library. And then we are importing something called fungible token. So this is a module that somebody created it. In this case, the guys from OpenZeppelin. So they are calling this fungible token module. So let's see where is that module. So this fungible token module, we can see here that it's two levels backwards. So we can see here that this is the fungible token module. So let's open it. And we can see here at the top that this is a module. How do I know it's a module? Because it starts with module, and this is the call of the module. Here in the contract itself, we can see here that we are importing the modules, and we have the constructor, which is the function to initialize our contract. In this case, we are just by starting the file, we have this module and the name of the module. We can think of module as libraries, right? We normally, when we write a code in TypeScript, we import libraries to use those functions that were implemented by somebody else. So the same thing here. Somebody's creating a library, a module called fungible token, and in here we're gonna have some functions implemented by the library owner, and then by importing that module, we're gonna be able to use those functions that are in these files now in the contract itself. Okay, perfect. So first, let's study what are the functions available within this module, which is called fungible token. So you can see here how this can be nested with other modules. So this contract is calling this module, and this module is calling other modules, right? So what are these modules? We can see here that they are importing from the utils, initialize, and utils. So these utils, we can see here that it's are this contract here, the utils. So this is modules that are going to be used by other contracts and other modules. So general modules, they are placing that under the utils folder. So we have source, and we can see here these modules, right? We have the initializable, we have here the initializable contract, and we have the utils. We have the utils contract. So let's open these two to see what we have inside. First, initializable contract. We can see we are using language 15. For all these contracts on all these modules, they are using this language version 15. So they're calling this module initializable. They are importing the compacts on the library. And okay, so now they are starting initializing declaring some variables. In this case, it's a ledger variable called isInitialize of type Boolean. And then we have some circuits that it's, for example, this circuit is called initialized, doesn't have any return. And what it's doing inside, it's calling a assert not initialized function. Where is this function coming from? If we go down here, we can see that that function, it's another circuit. So a circuit can call another circuit, right? So you can see how compact feels like TypeScript. We have functions that in compact we call circuits, and we can call functions within functions and be called by a constructor that in TypeScript we can think of a class, for example. So we call this assert not initialize. So this is a circuit, and what is this function circuit doing? Pretty much we are asserting. So assert is the way that we can assert things in compact, which are going to be implemented within the zero knowledge proofs. So we are asserting that is initialized, that it's of type Boolean. We can see here that we declared this as a ledger, is initialized of type Boolean. So if it's not initialized, then we pass. Otherwise, it fails with this message: initializable contract already initialized. And then we have another function called assert initialized. What it's doing? In this case, it's asserting is initialized and calling this function. So this module, it's pretty much a way to initialize a variable and then toggle between true and false, and a function, a circuit, to provide a way to verify if it's initialized or if it's not initialized. Pretty simple, right? Perfect. So this is the module that we have initialized, and they are calling another module, which is utils. So let's see what we have in these utils. In these utils, we have a module called utils. They're importing the compact standard library, and then they are declaring some circuits. We can see here that they are calling these circuits pure, and there are some other circuits that are not pure. What is this pure about? As a circuit is considered pure if you are not using any witness or any ledger. For example, this one is not pure because we're using is initialized, and this initialized is of type it's coming from the ledger. In this case, for example, we have this function which is pure. It's called isKey or address zero, and in this case, we're gonna see that we are not using any ledger or witness. So the argument for this function, it's key or address of type either. This is a type that we have in compact. So this could be a CSWAP coin public key, a representation within CSWAP, or a contract address, a representation within the Kashina protocol. And the output of this circuit, the function, it's a boolean. So pretty much we want to know if this argument is a key from CSWAP or it's address. How we do that? We're gonna return the isContract address function passing the key or address. Where is this function coming from? So if we see here, we have this function where we're passing some parameters as well, and we are just getting the key or address is left. So this is left is a method that we have for this type of either, right? So we have either this one and this one. This one it's called left and this one is called right. So in the method, we say if this key or address is left, meaning it's a CSWAP coin public key, okay, we're gonna return the negation of that result for its contract address. So if it's left, it means it's not contract address, right? Because contract address is on the right. So you can see here that during all this implementation, we haven't used any ledger or witness at all. We're just using the parameters provided by the inputs of the function. That's why all these functions are pure. Okay, so we have studied this first circuit of the function utils. You can see that we are learning how to implement these contracts, how to test them, what are the different implementations within Compact. So we're going to be studying these little by little. So you get to know Compact itself and how tokenization is going to work. So far, we haven't seen anything about tokenization. We are just studying the framework, the structure of those contracts from OpenZeppelin, and understanding some declarations within Compact. Okay, so this is for the so far for this contract of OpenZeppelin. In the next session, we're gonna keep studying these utils Compact. This is key or address zero function. But now, what I wanted to finish from the last session, it's running a transaction using the testnet network. So for that, we're gonna go to, so this is going to continue in the next session. We're gonna stop this for now. So now we're gonna go to the midnight started template. And in here, it's where we're gonna continue running the transactions. The setup process was explained in the last session, so we're just gonna continue. Make sure that you have Docker open, right? And we are gonna get into the CLI folder. So copy path, and we are gonna go to that folder. Excellent. In this folder, we have the package.json, and we were running the standalone mode the last session. Now we're gonna run the testnet mode with we are hosting the proof server ourselves. So for that case, we're going to use testnet remote PS. So we're going to call this script. We're going to run it using npm run testnet remote PS. So we're going to call that function. What it's going to do, it's going to spin up some instances. In this case, what is the instance? It's just the proof server. So if I click here, we can see here that we're just using the proof server. What's going on with the node and the indexer? Those ones, we are gonna use the ones implemented by the Midnight team and are hosted in the cloud. So we are just gonna point to them. But ourselves in our machine, we're gonna spin up just the proof server. So as before in the last session, if we enter here the proof server, we can see here that we have downloaded the ZK parameters. So now that we have studied the proof system, the different ZK proof systems, we now I think we better understand what these CK params are all about. We're using Halo 2, which is a implementation of we see here in the text here. See what that we mentioned that we are using these uh, Plonk and Halo 2, right? So this is the Halo 2 that we're using for Midnight, and the public parameters are these ones that we just downloaded. We have the CK params, we're using these parameters, and for syswap, it's already implemented, and we're using the specific cryptographic. So we see that we have the CKIRs, and we have the provers, and we have the verifiers for either for all these options: output, sign, and spend. Okay, perfect. So we have the parameters. So after implementing that, uh, sorry. Okay, we have run that command. I have already spun up our instances. So now we have the options of build a fresh wallet or build a wallet from seed. In this case, we're gonna build a new wallet. We're gonna build a fresh wallet. So we choose option number one. Number one. So now here we see that we have our seed, which is this number here, and the wallet address is this number here. And we are just waiting for having some funds, right? Because we know that this workflow happening right now, it's just our wallet was initialized and we're waiting just for funds to be received for that specific wallet. In this case, since we're using Testnet, that wallet created from scratch is not going to have any funds at all. We have to send funds to that wallet. In the case from standalone mode, we initialize our wallet using that specific special seed phrase that ends with one, where we have automatically from zero some funds in that wallet because we're using that standalone network. But for testnet, that's not the case. So we have to fund that wallet. So how we do that? We have different options. If you have a wallet in testnet with funds already, you can just send some tokens from your wallet to this specific address. Or the other way, it's if you don't have any wallet at all in testnet, you can use the faucet provided by Midnight to request some funds. So we're gonna do that. So we have our wallet address here. We're just gonna copy it. We're gonna go to the Midnight documentations. Midnight. So here, if we select Developer Hub, we're gonna have an option that says here need test tokens. I'm gonna say yes. I want to request some TDAST. So here it says, oh, wallet address required. So I'm just gonna input, I'm gonna paste that wallet address that I just copied. I'm gonna verify that I'm human. And then I'm just gonna request some funds. So this is gonna do all the process. The system itself in the backend is gonna create a proof and it's gonna send that funds to our wallet. So we just have to wait for the confirmation. So success, we have already requested, we have the transaction ID, and they have already sent those funds to us. So if we go back to the application, we see here that we're still waiting, right? Because they just sent the funds. Now we have to receive it, and the indexer have to and the wallet have to synchronize with our backend. See, now we have received the funds. We have received every time you request to the faucet, you receive 1,000 TDAST. So in the last episode, we studied these values that we receive from the wallet. We're going to take a look really fast. It's pretty much the same, but one point that I want to mention here is some differences between the testnet and deploy network. We can see here that the addresses now are implemented uh, with this with this framework. Sorry, with this standard, which is called Page 32M. So we can see here that this address is coming from Midnight. It's a shielded address, and it's coming from the network tested test. For undeploy, it appears here undeployed. And then we have our wallet. Then we have the available coins. We saw the last time that the coins are represented as index, nonce, type, and value. We have our balances. We have coin public key. We have our coins. The encryption public key, pretty much the same. We have is a shielded, but in this case, it's a encryption public key. Up here, when we saw the address, we see here that it's an address of testnet. Here it's an encryption public key of the network tested. So with Page 32M, we have some context to know what's going on with that address specifically. We have the nullifiers. In this case, we only have one coin public key. Sorry, we have only one coin. And then the pending coins, we don't have any, and the sync process has been synced. So it's true. So perfect. Now that we have funds in our wallet, we can deploy any contract or join an existing contract. In this case, since we're in testnet, if somebody else had deployed a contract, we can actually join that contract from that developer and interact on that contract. And deployed, we couldn't do that because those contracts were being deployed in our machines. We were hosting that contract. But well, right now I don't have any contract from other developers, so I'm gonna create my own contract in testnet. So I'm gonna choose option number one. So I'm gonna deploy a counter contract. We see here, if we go to the proof, we see here that the proof server received a request, and now it's proving, and it took 10.5 seconds to generate the proof. And that proof, it's been sent to the node. It's gonna be processed. When verified, it's gonna accept the transaction, and then the indexer is gonna take a look at the latest update of the ledger. And once that happens, we're gonna receive a confirmation saying, okay, we have a contract address. So this is the contract address. So if, for example, you were running this code right now with me, you could join this contract and we would be able to interact, right? So let's say what we can do with this contract right now. So since we're using the contract, we can increment or we can display. So if we choose option number two, display, the contract starts with 0. You can see here that it's 0. So we want to increment by 1. So we're going to choose now option number 1, which is increment. So we're going to increment. Again, this is going to request a proof to our proof server, and this is going to generate something here that we can compare with a standalone mode. Is that this time for generating the proof, it's pretty much the same, right? Since we're using our proof server hosted by ourselves. But the refresh time, it's much faster on undeployed because everything is being hosted in our machines. In this case, it has to travel to different instances in the cloud. But it's just small changes, right? There's nothing that's of a huge change. Okay, so after running the transaction, we can see here, and we analyze all this information on the last episode. We have the transaction hash, the transaction ID, the block height, and we have the public transcript, which is the program. And we have the section for succeed entirely, and we have our effects. We learned that in effects, we have claim contract, nullifiers, claim receive, claim expense, and mint. In this case, it's all empty because we are not creating any tokens. The gas is the cost for the transaction, and we have the program, right, which is it's written in impact. We don't have to write this ourselves. This is something that it's generated after compiling our compact contract. Okay, and then we have the foldable effects. We don't have any, and the private section. And we don't. All this is empty because we are not dealing with tokens. All these details we took a look on the last section. They haven't changed anything between standalone mode and tested mode. So perfect. Now that we have run the transaction, we're gonna see the current value of the counter. If we choose now, we choose now option number 2, we see here that now we have a ledger state 1. So we have successfully incremented our counter value by 1. Excellent. And now we can exit the contract, and we have run the transaction on the testnet network. And as a conclusion, we can see that not much have changed regarding the transaction process, but we can see that because we're using base 32M, we can see some differences on the representations of the tokens addresses. So we have a better context and some difference in the time that it takes for our circuits, our client to synchronize with the indexer, because the indexer that is hosted in our machine is going to happen way much faster, right? Perfect. So with that, we finalized the transaction creation using the CLI folder. For the next episode, we're going to start now to study the testing frameworks. Remember that I mentioned on the contract from Zeppelin that they're using some testing frameworks. So far, what we've done is creating our contract and then writing all the functions and implementing the TUI on this CLI folder to run the transactions. But this is pretty much like doing everything all together. We need to have a way to implement and test part of our code in specific phases. So that's what we're gonna do now. And the next session, we are gonna on the counter contract where we write our contract, we're gonna study this folder which is test, where we're gonna see a way to actually test this counter compact using just logic without having to deploy the instances. Perfect. So now let's go to questions. If somebody have any questions, I'm gonna enable the request option so you can raise your hands if you want to jump into the stage, or just write any questions on the chat. Um, I can see here that um, we have a question from Honrat. Thank you, Eric. Great session as usual. Not questions from me today. Okay, Honrat, thank you for the feedback. Yeah, we are going at paces. We're gonna get there that we end up doing these end-to-end applications, right? But thank you for the feedback. Um, I'm just gonna wait a little bit more in case somebody has any questions, any comments. I'm gonna see here if I have any questions as well. Okay, so here on Discord, somebody brought me a question regarding the hackathon. Uh, so I mentioned this here that we have this hackathon page, and let's see here. You go to developers, you have hackathons. This is the way you get to this page. And they were asking me where is going to take place this midnight hackathon in Buenos Aires. These midnight hackathons, let's get into the title. Let's see if we have. I can see here that we don't have any information regarding the midnight hackathons here in the title. But if you click here register, let's see what happens if you click register. See, If you click register, now you have all the details. So let's see here what we have. Midnight Hackathon Buenos Aires. This is going to take place in Saturday, August 23rd. This is the address of the hackathon. This is hosted by Diego, August, and the Midnight Foundation. So you can contact any of these uh, of these developers if you want any other information. They are public in Twitter. Next, uh, they have here some information regarding the event, the dates, and the prices. Right, we have five. They're gonna pay in USDM, which is a token in Cardano, a stable coin in Cardano, in USDM. The first place it's 5,000, 3,000, 2,000. Right. Mm, it's in Spanish, right? Because it's focused for people from Argentina and Latin America that speak Spanish. But as I mentioned, anybody can go. I mean, if it's okay for you to travel from other faraway country to Argentina, it's perfectly okay. But the apparently the main language that is going to be hosted during the event it's in Spanish. But yeah, um, let's see if I have here another question from Benja Martinez. Are you participating in the hackathon at Buenos Aires? No, I'm since we are collaborating with Edda Labs and Mesh, I'm not participating anymore on the hackathons. My main mission is actually to collaborate and help developers during this process. We can call it developing a DApp or participating in a hackathon. That's why we're doing these midnight sessions for helping teaching people how to develop in midnight or answer any questions or discussion that we can have. And for Buenos Aires itself, I was planning to go to provide some support to the organizers, but during that time, it's gonna be really difficult for me to travel to Argentina. So no, I'm not gonna be during that hackathon. Nevertheless, there is people are going Steve from the Midnight team, Alejandro. So we're gonna have people from the Midnight Foundation team itself going to that event. So it's gonna be a really nice event, Benja. If you manage to go over there, it's gonna be really worth it. Okay, great. Thanks. Thanks for the stations I'm going. Okay, Benja. Perfect. You have to send some photos so everybody can see what's going on these side events. Actually, I have the last time I went to a in-person hackathon was the Cardano Tech Week in Buenos Aires as well. It was in November last year, and these in-person hackathons are really nice. These events, it's the 2 months events, hackathons like the live events. It's really nice to learn how to write combat code, write applications, network, and go through the whole process with time and at your own pace. These 2 1 days hackathons, uh, I love as well the feeling because it's really quick, it's really fast, it's more ideation process, and you get to meet people, developers in that location specifically. So the networking, it's even better because it's really short time and everybody suffered together during the hackathon. Yeah, but yeah, for sure send photos. I will love to see those photos. I'm going. Sure, it will be crazy and cool. Yeah, for sure, Benja. Okay, guys. So well, thank you again, and we will continue next week with the other session. See you next week. Bye bye.